Counting operations is too cumbersome and too detailed. We don't need so much information. Let's find a more abstract measure that is more easy to obtain and gives us an idea of the complexity of a program. We will introduce the big O notation. Let's start with the definition of the big O notation. A function f of n is said to be order g of n, and we write big O of g of n, if and only if there exists constants c and n0 such that for all n greater than or equal to n0, f of n is not greater than c times g of n. So, simplifying, a multiple of g of n is always greater than f of n from some n0 on. For instance, the function 7n minus 3 is order n, because we can always forget about the coefficient. We have this multiplying factor c, remember in the formula? We also can always forget about the terms that grow slower. For instance, the function 20n cubed plus n times n log n plus 5 is order n cubed. Or in a polynomial, we just take the term with the highest exponent. The next function, 3 log n plus log n, is order log n, since log n grows slower than log n. Then if we have 2 to the power of 100 or whatever other number, this is a constant. It does not depend on n, which is very good. It does not depend on the size of the input. So we say that the complexity is constant, or order 1. And finally, 5 divided by n is order 1 divided by n. Here we see three functions graphically. A linear one, 50x or 50n in red, a cubic one, x to the power of 3 in blue, and an exponential one, 2 to the power of x in green. For low x's, the linear function is worse than the other two. But we are interested in the behavior for large x's. This is why we introduced this value n0 before. So we forget about low values in this analysis. We are interested in the asymptotic behavior. And we see that very soon the cubic function grows much faster than the linear one. And a bit later, the exponential function overtakes both and grows the fastest of all three. Of these three functions, linear is the best and exponential the worst. Here we see a comparative table of the different growth rates. Say we duplicate the size of the input n successively, 2, 4, 8, 16, 32, etc. How much do we have to wait for the result? If the algorithm is logarithmic, we barely have to wait much more. If it is quadratic or cubic, the growth is considerable. However, if it is exponential, the growth is unbearable. Can you even imagine how large the number 10 to the power of 38 is? For n equal 128, this algorithm is worthless. It might be correct, but you cannot wait so much. So try to avoid exponential algorithms. Here we see again the most important functions in the growth. At the bottom we have the logarithm. Note that it doesn't matter which base we're using the logarithm, since to change base we just need to multiply by a constant, and we forget about multiplying factors. So the logarithmic behavior is very good. Although it's not so good for small n's, the asymptotic behavior is excellent. Then we have the linear functions. Then come n log n, the quadratic and cubic functions. And we see again the exponential growth as the worst of all of them. This is finally another way of getting a better feeling about how good the different functions are. Now let's go back to operations and seconds just to see the different growth rates. Let's just look at the first and the last line for a minute. If we have a processor that can execute 1 million instructions per second, and we have 400 n will be 2500. But if we have an hour time, n will be able to grow linearly to 9 million. However, if you have an exponential function, like in the line at the bottom, the number n will not even duplicate, although we wait 3,600 times longer. As you can see, there can be enormous differences in the use of resources of programs. We were mainly thinking about time, but it could also be of other resources like space and memory. At any rate, we have to be careful to design programs that consume as few resources as possible, because the growth might be unbearable. A correct but inefficient program might be in practice unusable. Do you want to see me duplicate very fast? So let's do it exponentially.